All right, good afternoon. Here we are yet again for another lovely session of ENGR 2302, Engineering Dynamics. And this will be part 2 of Lecture 14 in the series. So, we have one more topic from Chapter 16 to cover, and this will be constrained plane motion. Constrained plane motion. Constrained plane motion. So what this means is, in most kind of engineering applications, you cannot just, a object is not simply free to rotate or move however it wishes. In many engineering contexts, a body is not completely free to move as it would. Is not completely free to move as it would, or as it would will. Free to move however it wishes. It has some degrees of freedom, but not the full set. But not the full set. For example, and a good example would be something like an axle in a power plant, or a drive shaft. Would be a great example. Maybe in a wind turbine, or a hydro plant, or something like that. In that case, it can only rotate. The only degree of freedom it has is single axis rotation. It cannot move, even if I put a force on it that would tend to move it left or right, it's going to have supports on it that will prevent it from moving left or right. So these are things like cranks, connecting rods, slipping wheels, etc. Okay? And so if I want to provide a definition, a more defined, or my explicit definition of this, constrained plane motion. Well, it's still plane motion, so it's still 2D. What this means is that we have motions with definite relations, between the components of acceleration components of the acceleration of the mass center and the angular acceleration of the body. The components of acceleration of the mass center, that's a more technical definition, and the angular acceleration of the body. All right. Okay, and we do begin our solution. We do begin by analyzing these via kinematic analysis, like we have previously. Okay, so another example of plane motion might be the kind of thing we've seen previously. So remember the previous example where we had the two sliders in their channels and then a rod connecting them. Remember this example previously? Wasn't that fun? Lovely. And so then we have a slider here and a slider here, and we have two pins on either end, something like this. And this should be a perfectly straight, perfectly uniform thickness rod. If it's not, there's just a lot of optical distortion in the room. Obviously, a lot of optical distortion today. It is raining outside, so maybe that's screwing things up. So this will be. I'll have a force P here, and I could then say if the center of gravity is at G here, I could have an acceleration in the x and in the y. I could have an acceleration in the x and the y, ax here, and ay here. However, I also have this angle. Let me label this as something. Let me put some dimensions on here. And this is really getting into the heart of what it means to be constrained motion. That definition I gave before was kind of odd, but this is how it makes sense. This is L, this is theta here from the center line, theta, and alpha, and we also have alpha and omega. Alpha and omega, some amount of angular acceleration and some amount of angular velocity. And the reason it's called constrained motion is that it is not free, it's stuck in these channels. In this case, A is going to be some function of theta, omega, and alpha. And here, this will be the same thing. It will be some function of theta, omega, and alpha. This is what it means to be constrained motion. It's going to be some function of these other variables. In other words, if I know what kind of angle this thing is at, I already know its position, don't I? Assuming this is a rigid rod that can't stretch or compress, if I know the angle this thing is at, I can find this one and this one. If it's just, say, floating through space randomly, I don't know its acceleration in the x and y. It can accelerate in the x and the y without undergoing any kind of rotation, couldn't it? If this thing is floating through space, I can just pick this thing up and move it like this, or I can apply acceleration upward, that kind of thing. But when it is constrained like this, these become locked together. So fundamentally, that is what it means to have constrained motion. Okay, so let us consider this then. Oh, and also let me, if I were to draw out the sort of free body diagram and kinetic diagram, it would look something like this. If this is point A, all right, let me do this point B, and this point A, I would have the following forces, and I'll just draw the rod as a rod or a stick here. I have then P and NA, P and NA, and then NB. And then the weight here at G. The weight here, with this being at point G, let me make clear, let me label that here. G, actually I did light green last time, let me do the same here. G and G. And then, so these are all the forces on this thing. And then I can say this is equal to the inertial forces, which will be acting through the mass center, or the center of gravity, which is MAX, MAY, and I alpha. I alpha here. Okay. So next, I would like to look at a particular case of constrained motion, and that would be non-sensorial rotation. Non-sensorial rotation, which means rotation about a point that's not through the mass center. So a simple example of non-sensorial rotation would be something like a door. Think of a common door, and if you're watching a video, I'm pointing dramatically at the door in the corner. Think of something like a common door. The centroid of the door is at the center of the door, the center of that rectangle. That's where the centroid of the door is, and halfway through the depth of the door, the thickness of the door. But it is, so in other words, if this was just floating in the vacuum of space and I applied a force to it, it would have to rotate about that centroid. Any kind of object that is freely rotating will always rotate about its centroid, okay? It'll always rotate about its centroid. However, that we don't like having doors like that. They're not that useful. I mean, you could see those like that, I guess. Sometimes, I don't know, sometimes you see those, like one of those revolving glass doors in hotels or something like that you sometimes see. But this here, your common door in a domicile or in a educational institution or in a commercial setting, whatever it is, most doors just have one hinge on the left and that left or on the right, and that's good enough. And however, we are forcing it to rotate about a point that is not its centroid. But in one advantage that anyone know one of the advantages of not having the door rotate about its centroid? Well, there's two disadvantages. There's one disadvantage. One is that you actually induce a vertical moment on the supports. So that means you need much higher, you need stronger hinges to hold a door like that than you'd otherwise need with, say, like just a simple pole going down the middle or a socket joint or something on the top and the bottom, because you do have to resist moments. But there is actually a great benefit to having the hinge on one side, and that by doing that you have the force required to open the door, because you're effectively doubling your moment arm length. So if you think of that. Okay, but anyway, let's consider constrained motion, non-centroidal rotation. So non-centroidal rotation. Let us consider non-centroidal rotation. Okay, so again, in this case, if I'm to define this, I will say that the motion of the body is constrained by some support. To rotate about a fixed axis that does not pass through the mass center. So normally objects like to rotate about their center of mass, but we're not going to let it. And this is actually how you get vibration in machinery. If you have a perfectly balanced axle or a perfectly balanced system, you won't get any kind of knocking or vibration in your disc or something, or in your machine or whatever it is, your drive shaft. And so think about people who design things like flywheels. There are certain companies that actually make flywheels, large flywheels, huge flywheels, for the purpose of storing energy. So that's actually kind of an interesting thing if you think about it. Like electricity, we don't really have the ability to store it in bulk. It needs to be produced at the same rate it is consumed. And so the electrical companies have all sorts of infrastructure to, when you flip a light switch on in one room somewhere far away, a power plant has to ramp up a little bit the speed of their rotors in order to generate a little bit more electricity, or they have to let a little bit more steam out of the boiler. They have to let a little bit more water over the dam. They have to do all of these things to increase the demand. Now, one way they can ameliorate that is to use flywheels, because flywheels are great because they're not as efficient at storing massive amounts of energy as, say, like a hydroelectric dam, but they are great in that they are very easy to ramp up and ramp down. So they're very good for fine-tuning the amount of electrical energy being delivered to the grid. And so a flywheel may just be a large chunk of steel or a large chunk of a composite material spinning in a vacuum at a very high temperature and elevated with a magnet so it has barely any force on the bottom of it at its support. And so that can be very cool. But those things, when you design a large flywheel, one of your primary problems in terms of manufacturing is balance. So if you're designing a flywheel to rotate at, thousands of RPM and with tremendous amounts of energy, huge mass spinning very, very fast, if that thing is not almost perfectly balanced, it is going to shake itself to pieces. It will destroy itself by its own rotation. So, this is something you actually want to avoid when often designing rotating machinery. But anyway, so let's say we have this. Now let me sort of I'll draw kind of a elliptical object, an ellipsoid of some sort here. And let's say I would normally like to have normally I would like to have my rotation be about G here. But I'm not going to let that happen. Instead, we're going to rotate about some other point O here. So we would like to rotate here, but we can't. So instead we're going to rotate here. And the center of our rotations, this thing's going to be wobbling around like roll, 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 roll. That's a technical term. It's just going to be wobbling around. Anyway, that's just a very poorly designed motor. Or, if you just want to design it properly, make it a structure and just weld it down. Sorry, but I am a civil engineer. I will always be a civil engineer, and I make mechanical students very annoyed when I tell them this, but it is true. A machine is just a improperly designed structure that hasn't been properly bolted down. Anyway, R. I promise not to put that on the exam. I just imagine a bunch of mechanical students sitting there, torn between answering the question the way the professor wants, or going with their heart, and so real ethical dilemma there. But I'm not going to make you do that. So anyway, let me label a couple accelerations here. I would have my tangential acceleration tangential, which will be R alpha. And I would have both an alpha and an omega. So let me say we have an alpha and an omega. So we have an alpha here, some angular acceleration, and also some omega, some sort of angular velocity. And the tangential acceleration is going to be r times alpha. You've seen this 1,000 times. And then the normal, or the centripetal acceleration, is going to be r omega squared. R omega squared. Okay? And so, one way to think of this is that we can collapse this down into a series of forces about a different point. Okay? So again, let me summarize this here. The kinematic relationship between the mass center G and motion of body about G, and the motion of body about O, I should say, well, this is going to be AT is equal to, just like I had before, R alpha, and AN equals R omega squared. R omega squared. R omega squared. R omega squared. Okay, so then we could use this to simplify this down and sort of turn this into some forces that are maybe we could create something that is equivalent to a rotation about the mass center. That's what we would like to do. We want to then find equivalent forces about the mass center, equivalent behavior about the mass center. And we could essentially use dynamic equilibrium. And again, it's going to come down to dynamic equilibrium here by saying all external forces must ultimately equal the motion, the inertial forces. All external forces must ultimately equal the rotational for the inertial forces about the mass center. And I think this is a bit difficult to visualize here, but so instead I am going to simply go through a few examples. Inertial forces about the mass center. About the mass center. Okay. Okay, so let us look at something, for example, rolling motion. Okay? Let us consider rolling motion. That is an example of constrained rotation. Rolling motion. This is another case. Well, if you have a balanced disc, we don't really have much issue. Well, except we still have constrained motion. But if you have rolling motion, I can say for a disc here, if I look at the forces on this, let's say I'm applying a force P to it. If I apply a force P to this here, and let's say I apply it so it's not passing through the centroid, so it will cause rotation, tend to cause rotation. So I apply a force P here. And let me label G in both cases. G and G. And the forces on here might be the normal force, friction, and W, assuming this thing isn't slipping. And actually, you know, even if this force P was passing right through the centroid, the frictional force is what would generate a rotation, because of the moment from that. And we would have I alpha. This is dynamically equal to I alpha and MA. Your MAX. Okay. Now, if I look at for a balanced disc, if I look at a balanced disc, well, I can say that X bar is equal to R alpha, or sorry, R theta, or here, so the position at a given point and the theta, or at a given time and the theta, or actually a balanced disc without slipping, assuming it is gripping the ground strongly. X bar is going to be equal to R theta. And of course, that we've seen this kind of thing earlier. A is equal to R alpha. Now, if you have rolling but no sliding or no slipping again, and be consistent. Well, I know that the force F must be less than or equal to the force of friction F. Actually, sorry, that shouldn't be F, that should be W. Sorry about the weight pointing down. The force F must be less than or equal, the frictional force must be less than or equal to mu static times normal, times the normal force, N. And A, of course, is equal to the same R alpha. And then if you have rolling and sliding impending, or in other words, rolling So again, if this is going to be rolling but there is no slipping, in other words, the bottom surface of the disc is not sliding along the ground, the frictional force must be less than or equal to mu static over times n. Rolling, but on the verge of slipping, you would have F is equal to mu static. So in other words, I'm applying the maximum frictional force possible, mu static n, and again, A equals R alpha. And then rotating and sliding, if you have rotation and sliding, well, in this case, you go down to the mu kinetic. So this will be mu kinetic times n and A, and in that case, A and R alpha are independent. This is an example of constrained motion because as long as this thing is sliding along the ground with no slipping, if the wheel isn't slipping, then A is always going to be equal to R alpha, the tangential acceleration this way, or the linear acceleration, the translational acceleration of the center of gravity is going to be equal to R times alpha. But the moment you have something that starts slipping is the moment that you're going to have that they become independent, that they lose their cohesion, and something may be rotating, which is going to be sliding on the ground like a block anyway. So there you have it. Now, what if I look at something, say, what if I consider an unbalanced disc? Now, I don't know why you would build such a thing. Maybe you're some sort of mechanical engineer and you're cackling in the night and thinking what kind of horrible things you can build, and you came up with this monstrosity. So, something like this. So I'm just going to take, because I'm insane, I'm just going to take a portion of my disc and cut it out because I'm just not a good, sensible person. And we have this origin here. This is going to be the point that, okay, this origin, because this thing is a wheel, is still a circle. It's still a circle of the same diameter, so it's still going to have to rotate about this point. However, because I have gone nuts and removed a portion of my circle because I'm some deranged mechanical engineer who doesn't know how to build things properly. Sorry, mechanicals. It's all in good fun, maybe. We have the G here. The G has now been shifted toward the edge. So as this thing rotates, this unbalanced disc, the centroid of it, the center of gravity is going to go, and that's the technical term. It sounds like a dying cat. Oh my God. So we're going to have a few things here. For the unbalanced disc, we're going to have AO, the acceleration of this here is going to be, it's actually going to be equal to R alpha. So this isn't rolling, it's actually rotating about this point. However, the acceleration of the mass center G is going to be AG vector is equal to, AG is equal to AO plus the acceleration of G with respect to O. So in other words, let me kind of label that on here. I would likely have something perhaps like this with AO here. If this thing was just rolling along, let's say this was rolling along the ground, sorry. So this would be AO here. And then I would have, perhaps, this would have the same AO here, in that all the components would be adding together here. Then I would have pointing towards O, A of AG with respect to O with respect to O normal, and AG with respect to O actually tangential. So again, this will be equal to AO plus A of G with respect to O tangential plus A of G with respect to O normal. All right, questions on that? Okay, let's consider that here. I want to work through that one. Okay, so questions on that. That's the basic theory for constrained plane motion, but we can work through an example or two as well. Okay. So consider this here. Example. Consider a sphere on an incline. On an incline. All right, so here, this thing is going to have weight G and it's going to be balanced. So we don't have some weird machination of a deranged mechanical engineer. Oh, that's a potato. Another perfectly spherical sphere.
It's just our eyes are lying to us.
Yeah, your eyes are lying to you, yes. Your eyes are lying to you. Don't trust them. No, we believe in alternative facts here. About centroid G here. And this is 30 degrees. And also we've always been at war with East Asia. Oh, wait, no, Eurasia. Sorry, that was what that was. And we've always been at war with Eurasia. Brave 1984 references, lovely. And this is going to be, I almost said Brave New World, not quite. And this thing is going to have weight W, sphere weight W, released from rest. This will be released from rest, and no slippage, no sliding. Okay, and find A, the min value of the friction, min coefficient of friction needed to prevent friction, needed to prevent slipping, needed to prevent slipping. B, the velocity of the sphere after it is rolled 10 feet after rolling 10 feet. And C, the velocity of sphere if it could roll down a frictionless incline, if the incline were frictionless. In the frictionless case, it actually wouldn't rotate at all. It would just sort of slide down. The only way it can ever start rotating is if there's some amount of friction to actually sort of apply a force to spin it back up, isn't there? So if you look at this from the point of view of forces, the normal force is not capable of causing this thing to rotate. Can you see that? Normal force is going to be applied perpendicular to the plane, and because this is a sphere, the normal force will not be capable of causing any kind of rotation of the sphere. The only thing that can produce any kind of rotation is going to be the frictional force. So if we had a frictionless or a sheet of ice or something like that was pretty close to frictionless, this sphere would not spin. It would just sort of slide right on down. All right, so what do you think our first step is going to be? Free body diagram and a kinetic diagram. Exactly. Joy. So I'm going to draw two perfect spheres. Yay. Beautiful. Thank you. Two perfect spheres. And I'm going to draw a local coordinate system that we'll be using. I'm going to define my x and y axis as such. X and y. And x and y. X and y. And then the forces on here, I will basically be transforming the theta. Instead of looking at this theta, we're going to be looking at the theta here. So also let me label G here. Let me draw G. Oh, that's not right. Sorry about that. I have to erase my perfect sphere. I want it to be the same as the other one. Sorry about that. Another perfect sphere. Slightly smaller, but slightly more perfect.
What? By definition.
How does something be slightly more perfect? So x and y here. Then let me show, we'll have the g's. Let me show this. I'll have a g here and a g here. And then I'll have W acting downward. And so the forces acting on this, I'll have W acting downward. And then the normal force acting in the positive y direction. And the frictional force will act this way, trying to slow the ball down. Frictional force here. And I'm going to assume that this thing is not flying through the air. Reasonable assumption. That's why this is constrained motion. So this would be simply MA. I'm going to let this be MA, where A is just AX essentially. So AY is 0. And then also we will have some kind of I alpha on here. All right. Oh, and also I need to include my theta somewhere. And where theta shows up is the angle of weight. So these will be both this will be horizontal effectively, this will be vertical. But my theta, I want to do this in green. My theta will show up here. This is theta here. Okay? So then the rest is just math. The rest is just math. So sum of moments about C will be equal to effectively the accelerations, or the summation of moments about C effectives. In other words, it's basically the moments produced by the inertial forces. And so this will be W sine theta, W sine theta R times R. Oh, that's a really bad sign. Let me just start that over. W sine theta, W sine of theta times R is equal to MA times R, MA times R plus I alpha. So why didn't the frictional force and the normal force appear in my equation? Because I'm summing moments about point C here. I'm summing moments about point C here. C is the point of contact. So C might stand for contact. And so C is going to stand for the contact point. And the normal force and the frictional force, their line of action both passes through that point. So they can't generate any moments about that. This is statics all over again. And then this here is going to be equal to MA. Well, this is M R alpha. I'm going to replace my A with R alpha times R plus, now the formula that you can look up in the table for the moment of inertia of a sphere is 2/5 mr squared. Mr squared times alpha is equal to then also mass is just W over G. W over G times R alpha times R. And again, I'm going to replace mass with W over G plus 2/5 W over G, W over G, R squared alpha. And this is equal then to W sine theta times R. Hey, look, www.dynamics.com. Anyway, I wonder what's actually at dynamics.com. I don't know. You can Google that on your own time. Anyway, or actually not Google it, just try it out. That's a dangerous thing to tell someone in a class, but anyway. But if you go and cancel out the W, you will find that alpha is equal to 5G sine theta over 7R. Over 7R. And then, so that's what alpha is equal to. And then I can say that A is equal to R alpha. So then if I substitute in alpha, I get that this is equal to, R times 5G sine of theta over 7R. And this is then equal to simply 5G sine theta, or sine of theta, divided by 7. Hey, look at that. That's the acceleration. Isn't that kind of cool? I think it is. So what this tells me is that the acceleration of this block, or of this ball, of this sphere, is independent both of the mass of it and its radius. Interesting. So it doesn't matter what it's made of, as long as it's maintaining, it's not slipping, that kind of thing. It could be, if I had a very large hill, I could have, imagine I had a very long mountain road or something like that. I could put a tiny pebble, a tiny like a tiny steel ball bearing, and a massive sphere of steel 10 feet across, and release them both, and they would roll at the same rate, barring air resistance and some other complications, but they would actually roll at the same rate. It's only a function of the gravitational acceleration and the angle, nothing else. So that's kind of cool. But it would go differently if this is on Mars or something. But anyway, that's something I love to do in some of my problems. Or just I love to do that in fluid mechanics especially. I'll just put a little sentence at the end of the problem that just says, "Oh, by the way, this is on the moon, where G is 1/6 of Earth," or something. It's oh so much fun. Anyway, it doesn't actually make the problems that much harder. But then, so this will be 5 times 32.2 times the sine of 30 degrees over 7, and I will get that A is equal to 11.50 feet per second squared. So that's my first quantity that I really want. The acceleration is going to be 11.5 feet per second squared. Next, I want to find the, well, I guess that wasn't really asked for, but I'll box it anyway because it's kind of cool. Then I need to find the coefficient of static friction. So my next task will be to find the coefficient of static friction. Okay, and I'm going to do that by doing a balance of forces in the x direction. So summation of forces in the x direction is going to be equal to max, which is just equal in this case to ma. And the summation of forces in the x direction will be W sine theta minus the frictional force F equals ma. And I know what ma is, or I know what A is, so I can say that ma is just W over G W over G times 5G sine theta over 7. And this is then also equal to W sine theta. And so here, then I can solve for F, and I will get that F is equal to 2/7, simply here, 2/7 W sine of theta. Or simply 0.143 W. So the frictional force is going to be equal to 0.143 W. Then if I do a summation of forces in the y direction, I will get that this is equal to 0 because there's no acceleration in the y direction. And I get that if this is n minus W cosine theta, W cosine theta equals 0. And so then n equals W cosine theta, or W cosine 30 degrees equals 0.866 W. 0.866 W. Then to calculate the coefficient of static friction, I can simply say that F, frictional force F is equal to mu static times the normal force. So putting this in for this and this in for this, I can get that mu static is equal to F, the frictional force, divided by the normal force, N. So 0.143 W. So thankfully my weight cancels out because I don't know the weight of this thing. Divided by 0.866 W. Weight cancels out, and I get that mu static is equal to 0.165. 0.165. And then if I want to calculate the velocity after 10 feet, well, this is now just a it's now a kinematics problem to calculate velocity after 10 feet. After 10 feet, well, I would just use Vf squared equals Vi squared plus 2a delta x, where delta x is 10 feet, Vi is 0, a is the 11.5 feet per second squared, and I can get very easily that Vf is 15.17 feet per second. Fairly trivial to solve. I won't work all the way through it. I won't work all the way through that. That is fairly trivial. But what I would like to do then is look at the linear acceleration if there were no friction at all. So let's consider that. If there were no friction, well, let's look at the sum of moments. So if I looked at the same sum of moments before, that previously in the only equals I alpha, remember that one? Now previously I found that the summation of moments is equal to what? Is equal to, let's see, previously I said that the sum of moments was based off of the, let's do the sum of moments about C, I should say, here. Now, how else can I express this? Oh, let's see. Well, if we're thinking about the rotation about there, so this is basically going to come to, well, one way to express this is that I know there's not going to be any kind of rotation, right? The only way I can get any rotation about the circle, about the point O, is through the frictional force. And so there's no because there's no frictional force, I know that alpha is 0 right off the bat. So I know alpha is 0, and because friction forces are 0, I could look at that. So perhaps another way to look at this is, well, actually it's a different summation of moments. I got to include the point. Previously I summed moments about point O, or sorry, about point C, the point of contact. Here I can sum moments about point O. And I would find that, fairly simply that the only force that can produce friction is the F times R, and then this is equal to I alpha. However, F is equal to 0, therefore alpha is equal to 0. So there will be no angular acceleration, therefore no rotation. This ball is sliding. So it's just going to make a very herp-a-derp slide right down the hill, very anticlimactically. I'm just going to go roll. Anyway, very technical term, I know. Then I can look and say, okay, the summation of forces in the x direction is equal to MA, and I can then say that W sine of theta is equal to MA, because previously we had the frictional force as a term in the x direction, but that's not there anymore. And so this is then equal to W over G alpha, or W over G times A. And then A simply will be G sine of theta, which is equal to 32.2 times the sine of 30 degrees, and that will come to 16.1 feet per second squared. That's the A, and then using the same VF squared equals VI squared and plus 2A delta x, I would find that the final velocity is equal to 17.94 feet per second. So instead of having a final velocity of 15.17, we would have, instead of having a final velocity of approximately 15 feet per second, I would have a final velocity of approximately 18 feet per second. All right, questions on that? So I think I'm going to let you out a little bit early for today, and that will be my just one brief example on constrained motion. All right, so I think that'll do it for today. I'll give you a few things after this, a few comments after this for the exam, but that'll do it, and thank you.